Okay. Hey guys, I'm Abdul Azeez. I'm currently working as a data scientist at NextSquare. And in Salstart, I'm a AI researcher, come generative modeling team lead over there. So that's my focus point. So today's topic is about facial emotion recognition, that is FER. So yeah, to get started. So if you guys have any questions or something, just drop down the questions in the question windows. I and Vivek will be answering them. Yeah. So yeah, let's get started. So what is the goal about the facial emotion recognition? So goal is here is to create a program that can read emotions of the faces present in the images. So the stuff is, it's like we can't tell the machine whether how a face will be happy, how a face will be sad, everything like that. So that's where this comes into consideration. So when you're giving the data in a specific manner, in a specific, like say when you're giving the input in the X in a specific manner and the Y in the specific manner, which is input and output, it can figure out itself like what are the characteristics which can detect an emotion. So that is the goal over here. So next, so where are the this one use cases for this everything? So emotion detection has been used in multiple scenarios. So majorly it is seen to understand the user behavior. So user behavior or kind of like a feedback system or something you can just think about. So few use cases have just dropped on. So which is like so with the autonomous cars and ADAS system. ADAS is nothing but driving assistance, automatic driving assistance like that. Yeah, let I check the. Okay. Yeah. Cool. Uh-huh. So use cases is it's like ADAS systems. ADAS stands for automatic driver assistance systems. So what this does is we have seen in Zoom cars and all. So what ADAS does is it's like when a new driver is coming into driving a vehicle or something, it provides assistance. What is the speed he's going? Like whether he's whether he's switching the gears in the proper time, he's braking properly, like this and all. So for this system, so it is very hard to understand how the user is behaving to getting adapted to the systems. For these and all, it's like it's very hard to understand. Like so, we need a real-time behavior. So for to understand the ADAS behavior, everything and all. So like we can't stick on to the reviews and all. So reviews is a collaborator. It's like after going on a drive using the ADAS system, test drive or something like that. After end of the day or something like that, only we get a review saying that like, oh, okay, the system is very bad, it's not doing well, that and all. But so that those feedbacks, it just says that it is bad. It doesn't point out where it is bad, where exactly it is bad, that and all. So to get to that point, that's where facial emotion recognition has been used and all in most of the cars majorly. So what they do is they fit up a camera in front of the driver, and this video is being captured throughout in a test drive or something like that. So if from that video we extract the emotions, so we understand, we get to know at which point the user is being sad, or he's angry, or he's in a fear or something like that, he's frustrated or something. So these kind of emotion and all gives a negative vibes, and we can point out where exactly the fault is occurring. Say that it's like most of I have seen in the Zoom calls like uh, intro to the ADAS. So when you just sit into the system, it's like you can't control the volume of the feedback, volume of the ADAS. So what that happens is it's not everybody listens to the higher volume, right? So I might listen to I might think that like high volume feedback system would be like irritating, or it's like troublesome to me to drive the way. So So that is a very small fact. It's like a very small uh, flaw. It is just to reduce the volume. That's it. They haven't put the capability there. So this stuffs, it's like these small stuffs and all can be identified directly from the emotion recognition. So this is one of the this one use case. Other use cases we have seen in interviews. So now we know it's like we are in this one COVID and Corona time, and everything is happening online. So even the interviews, if you consider also, all the interviews are getting happening in like online Skype calls, Zoom calls, and all. So and the agenda or the new trend is what it's like automated interviews. So like the HR people, they don't have time to screen through or take an interview to multiple people like hundreds and 200s and uh, shortlist them. It's pretty hard. So what they do is they have an automated interview system. The multiple, even if you consider Tesla also. The fun part is you sit inside a Tesla car and you give an interview like that. So what that happens is there are multiple questions a robot asks or something like that. So so what they do is they capture the video to understand the feedback of the user in a real time. Say that like if the robot is asking the questions, so in the example you can see like what is the engagement level, what is the candidate interview candidate, what is the how much is he engaging to the robots, okay, and is he irritated because of the robotic sound, or is he irritated by the robotic reply, or how much happy is he, and like how much is he enjoying, how much is he concentrating on that, everything like that. And so there are a few cases where you can identify whether what he's saying is actually true or not, or just like he's just repeating the words or something like that. And all. So these kind of analysis, everything can be found out from real time using the FER. So other parts is product enrollments. So if you think about products, multiple products are there. It's like if you consider a video game, or if you consider multiple products and all. So what do they do is take they queue up like multiple audience, many like 20, 30 or something, and to take the mean opinion score. So mean opinion score is not that great actually. It gives a score, but it doesn't give a full-time value also on that. So what they do is they allow the users to allow the audience to use their product. So let's take an example of video games. So testing for a video games, when a new game is on the market, so they allow the users to play the game. They allow the kids or whoever adults, or depends on the video game content, they allow them to this one use the game, and at the real time they understand they pick, capture the video and does the analysis. So over there they give a curative of like what is the percentage of happiness throughout the video games, what is the uh, like let's go with positive and negative. So if you consider happiness, surprise, like that and all as a positive impact, and fear and anger or negative as a negative impact. So yeah, but from the video analysis we can capture, we can get an insight saying that like okay, this product audience have it's like 65 percentage happiness, or 65 percentage positive, 35% negative, like these and all. So these insights give a lot of impact to the product as compared to a mean opinion score. Because see, when you compare to the this one audience rating or a human tendency to rate. See what happens, when when people are asked to rate between 1 to 5 or something like that, and so like that depends on the mood of the people. So when they are in a very good mood, they'll just rate 5. They'll not think about anything like that. They'll just rate 5. Or if they're in a very bad mood or something, they'll rate 1. So that doesn't give direct correlation or direct relations to the actual product. What is it? How is it? Everything like that. So we can't depend purely on the people's rating. So that's where this FER starts involving, getting involved to understand the feedback of the user, understand the your users and everything, how how actually the user has been feeling like that and all. Let's go with questions. So there are no questions. If you have any questions, kindly drop down in the questions tab. Okay. I think I'll get moved. Okay. Okay. Moving on. So how are we going to this one solve this one emotion detection? There are multiple ways there. So we know in AI we have uh, one way which is a traditional technique. You can consider as a statistical technique, and another next comes, it's like when you're automating a statistical technique and you're improvising. There comes the machine learning. So how machine learning works or something. When you're gonna solve it with a machine learning way. So how it's gonna get to done everything like that. So I'll explain. So this is the pipeline. As you can see over here. So these are the images. Okay. So these are the images which has been provided everything. So first and foremost for an emotion detection is cropping out only the face, because we know that it's like you can say it's like clearly say 95% to 90% emotion depends purely on their faces. Okay, so we don't need the whole body or we don't need the chest part, everything like that and all. It's like we don't need it. So first and foremost for any emotion detection is cropping out the face over here. So this is what is the crop face looks like. Okay. Now I'm explaining about the way which is or an approach which is followed in the machine learning way. So what they have done is, so there is something called facial points. So our face has around, it's like around 42 to 16. There are multiple points. Depending on the which algorithm you can take, it's like there are 16 points and 42 points or something. So this is the 42 points which is saying. So so it is a normal understanding. We know that, like, how do we understand the emotion? Like, as a human, how do we understand the emotion of the humans? Oh yeah. So we see the faces, we detect their emotion based on their eyes, eyebrows, nose, mouth. How is the facial facial structure, everything and all. So the same goes with the algorithm. So same goes with the for computer also. So this 42 points. So 42 points depicts all the facial points, which consist of all these stuffs, which is so this point is for eyes, and this is for eyebrow, this points and all, and this is for jawline, and this is nose and mouth and all. So what this happens is, and this is a complete, you can think about 3D mapping of it and all. Okay. So what are you understanding in this is majorly is by seeing the what is the position of eyes, the what is the position, and whether eyes is being squinting or eyes is being broadened. So one of the example is, say it's like if you are surprised or anyone any human is being surprised, eyes will be enlarged. So like eyes will be fully open as compared to a person who is crying. If a person is crying, eyes will be squinted. It's like it's almost closed. Eyebrows will be near to each other. So if you see over here, this the distance between these 2 points will be very less. And if you example of a smile, if a smile is there, then these 2 points, so obviously the teeth will be seen, or the mouth will be open or something like that. So the distance between the points between the mouth or the lips, if you consider, that will be big. So that'll be this one thing. So same thing goes with the jawline. If you consider of a jawline, when you see, okay, let's see the example of the surprise face. So over here, let I clear it. Yeah. So this is a surprise face over here. So if you notice over here, the jawline of this person or this image is broader as compared to a this one, a normal face. So this is a normal face. So jawline of this and jawline of the this one surprise face, if you consider, surprise face is jawline is being broader. So even so that's why the even the jawline also it leads to the emotion detection, everything like that. Do you guys have any doubts on this? Let's see the question panel. Okay, so okay, so now so first is, let's go over the pipeline. First is we take out all the images. Then after that we do this one, we crop out only the faces. So there are multiple algorithms where there are multiple models to do that, to crop out the faces, everything like that. So we had cropped out the face. Next is, what do? We do this one. We write an algorithm to detect the facial points. So to detect the eyebrows, eyes, everything. Okay, there's another question. Let's see. Are the 42 facial points fixed for learning by any model? You can say it is a fixed, since it is a, see, this 42 points is been it is a similar things. What do we do in a training and all. So this 42 points has been given to a model has been trained with multiple phases, everything, and the model has been trained, and it has understood that, like, it for, so how this 42 points is being detected, I'll tell you on that. So what happens is, in a model, while a model is being trained, this one output classes is being multiple. So output classes is left eye and right eye, left eyebrow, right eyebrow, nose, and lips, and jawline at the last. So these are the classes. When when training a facial point recognition model, what they do is, these are the classes. They pick up these characters like eyes, this and all, nose, lips, everything and all. So just think about the image segmentation model, how they do. They say similar to that. They segment just the eyes, send the photo, and label it as this one, eyes. And same thing goes with the left eye, right eye, and everything like that. So here they, so now we have classes. Now we have different parts of the faces. Next is, they write an algorithm to detect the points. So if you, similar to a segmentation point also, when you take the corners of an image, it forms in points. So these points are 42 points are okay. This number, if you consider, it is fixed. So it depends on our use case. There are multiple. There is a 16-point phase. There is a 42-point phase. There's a multiple 64-point, like that and all. So it depends on our use case. We can pick up. So so this is how it happens also. Did I answer your question? Fix for learning by any model. Yeah. Okay. Sure. Okay. Yeah. Let's move. Let's see the answer. Okay. Good. Okay, question has been answered. Any other question can drop down. So moving on. Now we have cropped the face. We have detect the facial points. We know exactly where are the parts of the faces which is found on, like eyebrows and all. We exactly know where is the location of that and all. Let it clear it. Now we have all these points. We have, see, we have the XY coordinates of all these 42 points. How are we going to feed it to the model? So the fact is, let's see the question. If a person is standing upside down, will this detect the face? So yeah, so it will detect the face. So orientation doesn't matter, because during the training the model, there is something called data augmentation. So data augmentation, what they do is they tilt the face. Okay, for the audience, let me read out the questions. The question was, if this one minute. If a person is standing upside down, will this detect the face? Yeah. So this was the question. So whether it is upside down or 45 degrees or 180 degrees or something, while training the model, this is generally phased, or generally we do that in the computer vision is what, like we do data augmentation. One of the option in a data augmentation is shifting the phases in multiple angles. So that time what we do is 0 degree, 45 degree, 90 degree, 180 degree. So 180 degree is nothing but is a upside down phase. So while training, this is being provided. So the model is clearly, it knows that like which is a what to say, right position, or which side is the correct way. So it knows that eyes come at the top and nose come at the bottom, this one in mid, and lips come at the bottom or something like that. So it does detect. There are libraries. It's like when you are not doing data augmentation, it will not detect. But when you're doing a data augmentation and training a model, it will understand that which is the right form of a face, everything. Cool. Hope I answered that question. Okay, moving forward. So okay, we have 42 facial points right now. So when how will we give this XY coordinates to the machine learning algorithm? So this is an SVD. So this is SVD. So before that, there is something called feature extraction. So in a machine learning way, we definitely need a feature extraction. We have to say the model. We have to pick up which are the features to be given to the model. That's what is there in. That's what is the difference between a machine learning and the deep learning, if you consider. So we have to clearly see. So how are we going to provide it? So one is, well, there is, if you consider a whole face, there will be a center point of a face, if you consider. So one of a basic way, if you consider, what they do is they draw a line between all the points to the center of the face, like this, of the face, everything. So what this happens is, and these Euclidean distance, or you can say any kind of distance, depends on the face. And if you are having a 3D image, then you'll not be using Euclidean distance. You will be using the what is it, cosine angle. So with an angle. So yeah, you'll take a 3D distance, you'll not take a 2D distance. So very basic way is like we see it as a 2D image. It will be a photo. It will not be a 3D photo or something. It will be always a 2D photo. In that way, what they do is we take Euclidean distance. Euclidean distance is nothing but, if you consider, let us say this point is as x comma y, and this is center, which is cx comma cy. I'll change the color of the pen. Okay, this is better. So what is a Euclidean distance? Euclidean distance is a very basic thing, as we have seen in math and all. So it is nothing but this one difference of the x and y coordinates. So this one Euclidean distance will be cx minus x1 and cy minus y1. So what will this give? This will give the distance, or the how far is this point away from the center. So let us say this is the jaw position, jaw spotting, or you can consider ear position and all. So how far is this point as compared to the center of the face? This goes with multiple. This goes with all the points, everything. Here also, if you consider this and all. So we know for all these 42 points, how far is it from the center of the face? So using this, when you put this distance, or when you put this feature into the data set, that becomes x. So x is nothing but a Euclidean distance of all the Euclidean vectors of all the 42 points from the center point. Okay, you right now you have a 42 feature data set. Now it is all about just labeling them, saying that like, okay, this 42 points resembles to surprise phase, happy phase, that phase. So now we have found out this one. feature extraction. So we know what are the features to be detected, everything like that. So that we have found. Now next is all about we feed into a this one classification. So this is a classification problem where we say it's like whether whether the image is belongs to any of the label or not or something like that. So this is what. So there are multiple algorithms which can be used over here, which is like random forest or so. This example is a SVD, what is seen in the photo. So what SVD does is, if you guys don't know, I'll just explain. So what it does is all this 42 vectors, 42 features, uh, it plots on a this one 42 dimensional plane, and its SVD is a it what it does is it tries to um, draw a plane which splits in the 42 dimension. So in a feature dimensional, if you think in a very big dimension, it draws a plane. It finds a plane, or you can just think about the 2D. If you consider 2D plot, it draws a plane or a line which splits the two classes. In our cases, we have 7 classes, so it draws 7 planes to split that. Okay. So this is one of the basic way or generic way which is being used or something. So there is something called like say that like you want to improvise your emotion detection to a very high level. That time what do you do is like you go for higher points. You go for a facial map or something. So this is called something facial map. So these have multiple points, everything like that. And it's not only points. Okay, let I answer the question. So 42 features are the Euclidean distance of the, yes, yeah. The question was, so 42 features are the Euclidean distance of 42 points and the center. So that was the question. Yes, it is. That is a basic way of approaching like that. So there are futuristic way, multiple ways to do that. Okay, yeah. Cool. So other way is, this is what is a facial map. So facial map is also what happens is this is not a point. So in the facial map, it is not a point. It is a, you can think about a vectors or lines or set of lines or something. As you can see over here. So here it is all points are there, but here if you consider it is all lines over here. So let I erase and do it. Okay. So what happens over here is we know the structure of the lips, everything and all. So what people have understand is like from the facial points, it was detecting, but it was not fully perfect or something like that. So that's why they started to draw tangents and draw lines, everything like that for a face. Considering there, so this is nothing but like you can think about the curve fitting. So lips is a curve. So if you consider lips is a curve, right? So uh, if you consider a curve, there are multiple points. There are too many points involved in a curve, and there is too many angles involved in the curve. So that will create more multiple features, and it will start either the model will not learn at all, or it will start overfitting the model. So general, this is what is saying. So what they do is they do a curve fitting. They pick up points. They pick up points like in a facial points, how we did. They pick a point in a right way and a right position and draw lines such that the if you say think the curve is like this, and the what is the best way to represent this curve with just 2 points is one is this way. Either it's like draw a straight line for that curve or cross the curve. I'm sorry for the wrong drawings. Let us go. This is the curve. So one of the ways, take these 2 points and just join it, or go in a median of the curve and draw a line. So exactly in the, so midway of the top position and the bottom position. So midway you draw a line, or at the bottommost position you draw a line. So over here, if you consider over here, it is in the midway. So this line, if you see, this line is a midway. midway drawing. So this varies. This varies by person to person, and it is not a proven fact when to use center, when to use at the end or something like that. So okay, now we have a facial map. So now we have a facial drawing. We have removed all the curves. We have only the lines. Only the lines. Now what we do is every single line is a feature. Every single same thing. It's like 2 points distance of that becomes a feature. So all this facial map completely becomes a feature, and it's fed again to a machine learning algorithm. In this context, it will not be a 42 feature. It will be more than 42 feature, because there will be more than 42 lines over here. And one more thing over here is these lines are not all connected to the center point, if you notice over here. So if you see the this one portion of if you see the lines, the eyes or like that and all, so it's not connected to the center point. It is purely isolated. by because it is isolated, we get the original position of the eyes and what is the exact state of an eye, state of a nose, state of an lips or something like that. So it's not like fully dependent on the center face and so this gives the how do you say uh, yeah, so this gives a positional intelligence or localization. There is something called localization. So when you clearly you can tell that like what is the eye location and what is the eye feature and how is it, just because of this lines has been localized only for the eye and only for the left eye, only for this one. So if you notice a left eye, how will they find out this? It's by these features. So but from the nose only they find out whether it is a left eye or a right eye, something like that. Okay. Okay, hope you guys understood this way. I'll just wait for 5 minutes for any questions over here before moving on. So if you have any doubts in this facial map or facial points or how it is passed to an algorithm or what kind of algorithm, any kind of doubts, kindly drop down before moving on. So the next topic will be a deep learning way, how to approach that. So that will be in a totally different way. Okay, let's see the questions. How do you put facial points in an image? Okay. So yeah, that's what I had explained, right? So previously, um, see, there are multiple ways. One is, if you think of traditional way, in OpenCV, if you consider, they have written equations to generate these points. One is, so wait a minute, let me clear it. So if we are doing it on our own, what we do is we label. We first, this is the whole face. The complete face is this. We don't give the complete face to the model. To detect 42 points, you split the 42 points into multiple categories. So 42 points belongs to, say, lips. So lips is not 42 points. If you notice, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18. Yeah, so 18 points consist of lips. So we don't directly detect 42 points. First is we detect this 18 points. For that, what we do is similar that is, it's like first we detect, we crop out only the lips. So just the lips, we just crop out, we send it to the system and we get the endpoints. We train the system. How do you say, like, so image segmentation, it's like we segment the image, we segment this points like this, and these are the endpoints. These becomes the labels, and we train them. It's like not to think in a very vast manner or something. So we just create an equation in an image processing in an OpenCV way. So we create an equation to detect these points, or you can think about endpoints of this. This is the outermost layers, right? So we, uh, so the as I was explaining, curve fitting is. So first is we draw the curve, then after that we fit the curve. We fit the curve with different points over here. Then we get 18 points. See, the facial or the facial points input features or connecting lines be the input features. In facial map, it looks different algorithm used. Neighborhood classification, what are the different algorithms used for each process? Okay. Yeah. So there, as I was explaining, it's like there are two way. Well, the facial points is a traditional way, and the facial map is uh, it's a new way, or you can say um, improved way, advanced way of using over here. And correct. So if you consider a machine learning way, this is how the features being passed into it. Yeah. So like you can this one feed an image to the machine learning algorithm, right? So you have to feed it as a vector only, and generally if it is an image, if you consider as a vector, it will be a very huge high dimensional vector, and we have, it is not a advisable way to send an image as a vector to a machine learning algorithm. So that's why we send the distance or Euclidean points or facial maps or something to the machine learning algorithm. Okay, sure, cool. Let's get moving on to the deep learning algorithm. Okay, let's clear everything and switch to the next slide. Okay. Okay, now it is a very famous one, and we like a lot. Is how we gonna approach this problem in a deep learning way. Okay, half of the pipeline is same. How it is this is the input image. We have an input image. So there is something called there are multiple algorithms to detect the face. So here is something called I have used a Harkasad to detect the face. I have detect the face. Okay, let us see. If I want to prepare this type of data set, is there need to do manual or we can do automatically? So you don't need to do anything manually because there are multiple algorithms and there is multiple pre-trained models and libraries to detect these facial points or the faces or everything like that. So this face detection uh, generally or globally it is being used as a Harkasat. So Harkasat is being used in multiple things. So Harkasat is you can just import that Harkasat and crop out the face. So you have the input image, then you detect the face using the Harkasat. Then after that you feed into the CNN or yeah. So we know that for images we use convolution neural network, which is nothing but CNN. So that CNN has been explained over here. So let's this yeah, okay, so so the question was it's like can we use a facenet or a mtcnn or something. The fact is you can use anything, literally anything. It's like, see, for emotion detection one is uh, we don't need high end features and all. So if you consider the facenet or mtcnn or there are multiple features which consider for what to say color of the image and there are so many hidden features. There are so many features which are not required for emotion recognition. First is one of the way you just think it's like very basic thing is color of an image. Whether the person is there in grayscale, black and white, full color for HD resolution, full HD or full colored person or a black and white person. For an emotion, it doesn't depend, or we don't require the color feature at all. Whereas if you consider a FaceNet or MTCNN, color feature is a very high feature and it's being used in, so in there is a high weightage given to this one color of the image. So this makes this one image or the model get overfitted towards the color. So let's go with the next. Okay. If I want to prepare this table, okay, for the face it is okay. Already data sets are available. But if you want to detect other parts, how can I put data points in image? Other parts means other than faces. Okay. One of the ways, like if you want to detect the ears or something. So how we do it in a so how we do it normally for a classification is we do segmenting, right? Or if you think about painting, just say there is okay. I want to detect the teeth of this female. So before giving to the model, what do I do is there'll be people who color the teeth of the like this. Oh, I'm sorry. Yeah. So there is something called segmentation or coloring the position. Okay. Now this model is being so this image is being fed. Will crop out only the lips and we color the teeth of the female. Then we send it to the model. Then to detect these teeth, everything. Then after that, you do a so there is a mathematical model which does the curve fitting. So these curves are there, right, in the teeth. So these curves are turned into a um, facial points, that is points, or you can think about first is lines. You fit the curves with multiple lines such that complete teeth has been identified, or complete position of the teeth, everything is being found out. So that's how we do it. That's how the model has been trained out. Hope this answers the question. Moving forward, yeah, let I erase the drawings. Okay. Okay. So when the phase has been provided, uh, send it to a CNN model. So one of the way we can use is VGG16 is a good model to use, or your pre-trained model to use in this, or you can build your own CNN for that. So generally what happens is you use a VGG16 on this image, then you clip out the last two layers, everything. Then after that you put a fully dense layer and you get, so these are the fully connected layers. So the last dimensions will be 256 and final will be 7 dimension. So 7 outputs will be generated. For 7 outputs is nothing but 7 emotions, which includes of anger, surprise, everything like that. Okay, so like this and all. Hope this understands. You have any doubts in this? So I can explain the architecture, everything like that and all in the code demo. Overall, to say everything, it's like for emotion detection, what they do is they use a BGG16 plus fully connected network. And what we have seen is it's like it gets overfitted. So they tend to use a for this one convolution architecture um, of VGG16 of only the first 6 layers or 4 layers or something like that. I'll, why two fully connected? Also only yeah, it's like so that's what we do. It's like our output labels are 7, right? And this one after the max polling we get 128. Either we can 128 directly, we can put into 7. This is we are just making a upper convolution to get. So first is max polling of the layer is 6 cross 6 cross 128. Then we do a fully convolution or fully connected to get a vector of 128. So 128, then again we are increasing the dimension and then after that contracting it. So there are two ways. One is it's like you can directly convert to 128 into 7 labels, 128 dimension, and directly connect to this 7 labels or a fully connected layer. Or so we have seen, or it is seen in the seen multiple scenarios that when you do when you increase the dimension, you get the hidden dimensions also. So that's there. Okay, what is first one? First one in 1 cross 1 cross 7. Okay. So 7 represents the 7 labels. So there is something called happy, sad, surprise, multiple emotions, and there is neutral also. There are 7 labels or 7 outputs for an image. So this 1 cross 1 cross 7 means the vector or yeah, it is a vector. It is not a matrix. It is a 1 cross 1 cross 7, a 3-dimensional vector of 7 dimensions. Sorry, 7 labels. So endpoint, this complete image will be 48 cross 48 cross 3. This image or this pixels will be convoluted, then fully connected. Then after that, final end layer should always be at the dimension of your number of labels. So number of labels is equal to 7. So always the final layer should have the dimension of the number of labels or number of outputs. So in our case, we have number of outputs as 7 outputs or 7 emotions. So that is why the final layer is always 1 cross 1 cross 7. Okay, I'll wait for 5 more minutes to ask for any questions or something. Kindly drop down. Okay. Let's see the questions. Okay, this is okay. Cool. Okay, there are no questions. I guess let I move on. So, okay, let I go with the proceeding of how we are gonna solve the problem, everything. So, one is it like what is data and how important is the data? So, in emotion recognition or any classification algorithm, if you consider, we need a proper data. Good data is needed to get good results in machine learning. That is a stuff like throughout. We can't deny the fact at all. And in this case, we need a variety of phases. See, always remember that in a machine learning model or AI, we don't need quantity, we need quality or variety of the data. We don't require the same data getting repeated. 1,000 images are not required. 1,000 variety of images are required. So that's why. So if you consider a sad face, 1,000 varieties of sad faces are required. We don't require a sad same emotion or a same expression 1,000 faces or like that. So that's what this makes sure that our program can recognize the emotion from face it has not seen before. So that when we have more variety, the model understands very much understands more clearly, and it performs very well in the for the phases which was not seen or something. So for your phases and all. So let's go with the. I was talking about 7 labels, right? So the data which I have used is a FER 2013 data set from Kaggle, which has 48 cross 48 cross 3 dimensional this one images, which has 7 emotions, namely angry, disgust, fear, happy, sad, surprise, and neutral. So neutral faces, there is no emotion, just like neutral face like that. So if you consider here this is a neutral face. Yeah. So this is a neutral face and this is a surprise face. You can consider this is an angry face or a comedy face. Yeah, anything. Yeah, cool. Let's get moving. Okay, let's go to the next. Okay, so data pre-processing. Data pre-processing is required in everywhere. You consider machine learning or this and anything, any data you need pre-processing. So first and foremost is the rescaling of the data set. So rescaling of the data set is basically it's like you scale the data set. The data sets generally for image, if you consider it will be 0 to 255. We don't require 0 to 255. And that's why we do a rescaling of 0 to 1 or -1 to 1 that. So there are multiple ways. One of the ways in our case, mean removal will not be a ideal way. So rescaling or a normalizing will be doing it. And next is we have 7 labels. So instead of going label encoding, we can choose one hot encoding. We'll be doing that only because the labels are lesser. It's only 7. So it is just 7 cross 7 vectors will be created one hot encoded. So input will be normalized, output will be one hot encoded. Then yeah, that is the pre-processing we'll be doing it. So final is so this is the data model pipeline which has been shown everything, how it's gonna proceed and all. So you take the input frame, then after that, uh, yeah. So you get the input or the frame. So in case of a training data, it will be an input image. In case of a this one, what is it, testing, it will be a video. So it will be a frame. So each frame is sent. Then after that, feature selection has been given. So feature selection is nothing but the everything. Our cropping out the faces, then getting the facial points. In case of a machine learning approach, then if this feature classification selection will not be there if in case you are using a deep learning approach. So for a deep learning approach, feature selection will be only cropping out the face, nothing else. So then feature classification, then send it to a so this face database and all, it's like for face recognition that is not required. So to detect whether it is my face or your face or whose face, everything, and feature extraction from that and all. This is not required in our way. We can do it if you want it. So rest of it, it's like after selecting the feature, you run the model. The model can be a machine learning model, which is a support vector machine, or a decision tree, or a random forest classification algorithm, anything, or a deep neural network is as a CNN or a pre-trained model like BGG 16 or something. Finally, you run the model, you get the results. Then after that, you validate the results. So this is how this data modeling pipeline will be there. Cool. Okay. So yeah, that's here. Before going into the demo, just wait for few minutes to answer your questions. Any questions? Any clarification required? Uh, okay, let's go for the questions. Okay, move forward. Um, sure, fine. Let's go with the code demo. So Vivek, how do you think it's like? Shall I this one explain the demo, explain the code before executing, or we do it
So
parallelly?
let's share the collab link, the notebook link, and let people try to run it first. Then you can walk through it little later.
Oh yeah, sure. So are you saying we'll take a break?
No, not taking a break. You please share the notebook through chat here with everybody, and let's
Sure,
all
sure,
run that code. Okay.
definitely. Okay.
See, one thing I wanted to ask Abdul, what if the eyes are dislocated? Did we discuss that? Let's say
Dislocated. What?
the two eyes are, one eye is on the cheek.
Huh.
So,
So
yeah.
so the stuff is like when you do a facial map or this one 42 points feature. So what happens is this one each point we are defining the distance. So these points are recognized by the distance between the center of the image. So when we know that this one for a eye point, it will be certain distance from the center location or from the nose. If it is not at that distance, that face itself will not be detected.
Yeah, so Dr. Geoffrey Hinton had invented capsule network to solve that one. So are we solving that here without capsule networks?
No, that is purely advanced. So over there is uh, that is an advanced algorithm uh, which was seen. It's like from it was detecting faces from different texture and all. So since this one, if you consider Harkasad and all, Harkasad doesn't care about the facial structure or what to say, how a face looks, or color of the image, or texture. Yeah, the right word to say is facial texture. So Harkasad doesn't care about the facial texture and all. Because um, at the end, when the this one image is when the image has been dropped down, processed everything, finally it will be just a white and black and white points, and just by the lines. So eyes will be a straight line. Maybe I can explain that. One
So
minute.
it is basically checking distance to a center point.
Correct. You guys can see my screen, I guess. So what Harkasa does is, this whole image being processed, then it will come into a very low dimensional, and this whole eyes will become one single line. Which
Mhm.
eyes will be squinted to one single line, and nose will be one single line. Eyes will be in one single line, and eyebrow will be one single line. This and all. Same thing with the lips, everything. So what happens is, just because it becomes into one single line, and what it'll know that it has a equation which says that it having a threshold saying that this line should, the nose line and the eye line should be this at least this distance apart. Then only it is a face, like that. So it is a pre-decided or predefined equation which decides that. So over here, if you consider image, this one color of the image, facial texture, whether it is a skin or not, it doesn't take care, because uh, because this runs faster, and it is more easier. They wanted to make it as a simple algorithm, and it does runs for a faster processing, like that. But
What is
what
it
we
called?
sorry,
Harkasar, you said Harkasar? What is the term?
Harkasat is algorithm.
Okay.
It's available. I'll explain. Hazard is generally used for this one to detect the faces. So it is an open survey or a HAR like. So it is a mathematical model which does that. That's it. Hargasad. It's not a dynamical model or something. So for face recognition with anything, they use a Hargasad one. That's it. So this is the problem. What they have seen is what you was talking about. The problem they have seen is it started detecting faces in what to say, in different textures. It started detecting faces in case of stone. If the stone, if something carving is there, some carving which looks like a face, then it will detect as a face. It will not care whether it is a this one skin is there or not, whether it is a rock or whether the texture is a skin, is it a human or nothing like that. Because even the rock, if it is having the features of a face or of eyes, everything like that, it will start detecting it. So that's why advanced algorithm was built up where you spoke about. I'm sorry, I forgot the name. So that was improvised, and that takes care of the skin texture, color, everything like that, and all. And say at the
Capsule,
same time,
capsule network.
sorry.
Capsule.
Yeah.
Capsule network.
Okay.
So instead of Har Cascade, I could still use MTCNN, which is a face extractor, right?
Face extractor.
MTCNN is a face extractor actually. We use it with along FaceNet is a face embedding, and MTCNN is a face extractor. So Har Cascade seems to be OpenCV, whereas MTCNN is a deep learning model.
So there is a catch. One is that, like, you want it fast or you want it accurate. If you want it fast, Harkasad. If you want it accurate, then you go with multiple face recognition algorithms like MDCN and FaceNet, everything. That's the reason. It's like
Okay.
That only depends on the use case, and if you want the model to be heavy, if you're okay for the model to be heavy and it should be very accurate, but you don't care about the frame rate and all. You're okay if the output is coming after 10 frames, 15 frames, and the response is pretty slow or something. Or if you're doing a post processing, in case of this one in ADAS system or video games or all video analytics, what they do is they don't do it real time. They send it to the algorithm, say this one FaceNet and MDCN and everything. Generally, the response time will be like 5 seconds and 6 seconds or something. So they do a post processing. So they don't do a real time. They feed the video into the algorithm and they allow the model to run and process its own own. Then after that, get the analytics of it, everything. So this is the post processing. That time you don't require it to be a real time. That time you can use MTCN. Okay. Let me answer a question. Harcasar only detects 2D faces. Yeah, correct. Even that's right. Yeah. Harcasar detects only the 2D faces, not the 3D faces. You can provide, you can feed only the 2D image to it. You can't provide a 3D image to it. That's right. Yeah, cool. Let's move forward. I'll provide so the link will be provided by Vivek. I'll send the link to Vivek. Um, I'll send it on the group. Vivek, I shared on the group. Kindly share it to the audience.
Yeah, I'll do that. So audience, we have sent via chat the GitHub link for Abdul's code. You can download this to your local drive and then upload to your.
No, actually, that's not required. Just see here. I'm just hope you guys can see my screen. So there is something called emotion analysis. Just click on it. Go over here. So you'll get options like open and collab. So this is a button. So just click on this, and it'll open and collab. You can run it over here, and if you want, you can take a copy of it also. It gets attached. I'll show you how is that. Yeah, we can just see this. So there is an option called copy to drive. You can click on it and copy to drive it, drive, or you can run the code on your own. You can run it over here also, it will get run. No problem with that.
So all of us will be running your version of the code.
No, yeah, it's like I have given as a open access only. Maybe they'll not be able to edit or something like that. Or even if they're editing, it will be saved in their buffer. It will not be saved in my buffer. So it will not affect anyways to me. Not a problem with that. So you guys can just click on this and copy to drive for your.
You can also fork it to your GitHub. Yes.
No, sure. You guys can fork it. So if you're forking it, there is something called Open Notebook. So just open collab, then open notebook, and directly your this one GitHub link. You can open the Python file, Python notebook from that also. So whichever you guys feel, you can do that. Feel fine. So generally, stuff is there are only 3 files are there. So one is emotional analysis, which is the collab notebook. You can run it on collab, and this one real time emotion detection py is a if you want to see or detect faces in a real time, then you have to run it in your local machine, because I haven't wrote the code to fetch this one webcam details from the collab. It's not safe. It's not good. So I haven't done it. So you can run it from your local environment. So there is a requirements.txt file. It contains this one libraries. You don't require much. You just require OpenCV, Keras, and TensorFlow 2.0. That's it. And just create this one Anaconda or something, just run this requirement file, then just Python real-time emotion detection.py. Run this file, you will get a real-time emotion detection. Yeah, everyone try to do this. I'll wait for some 10 minutes or something. Mega is a cloud, just like Google Drive. So this is what, if you want, if you guys are interested, just go forward and this one. So this cloud, so this has an I like this cloud just because it has a CLI to upload and download files and all. So it is much simpler and all. So that's what I'm installing. So the library is mega.py is pip install. So I downloaded the library or the CLI if you consider. And next is download and setup of the working directory. Okay. So first is this one. So this doesn't depend on which directory you are, whether it is you're in a drive or something like that. So it just creates in one folder and all the files gets downloaded over there. So what it is, first option is if the emotion detection. Let I go with this question. Can you share the mega as well? No. See, mega.py is not a file. So it is there in the pip libraries. If you want to download it for on your system also, just give this command. This mega.py, it's not in my local machine, or it's not there in my collab or something. You can just run this command, just like pip install TensorFlow, pip install mega.py. It'll get downloaded. That's it. Okay. Yeah. That sounds right. Okay, the question was, sorry, I was, if emotion detection is not in the list. So what this means is, I'm creating an directory which is emotion detection, and I'm just checking if it is not there. If the directory is not present, then create it. That's it. Then after that, I'm changing the directory to the emotion detection. You can see over here. So this one directory gets created over here. Next is, now it is all about downloading all the data, everything. So how do you access the CLI is simple. From Mega, import Mega. That's it. Then you create an instance of the Mega CLI. Then you create a anonymous user login. So in this, you don't, since I have given a public access to these files. So you can just, you don't need to create any account in Mega or something. You can just give mega.login and it will just create an anonymous user, and you will be logged in. Or if you want to do anything private works or something like that, it's like file uploading or something, that time you give the mega.login and username, blah blah blah. But username, password, everything like that. So that's it. That's it. Next is, so I have given saying that don't cancel while downloading, because it will take some few time to download. This is pretty much big files, so it gets it takes time depending on your bandwidth, Wi-Fi bandwidth, and all. That's what is here. So first file is model structure or fer.json. I'm sorry. Yeah. So model structure is the CNN structure. So this is for testing purpose. So this gets downloaded fer.json, and that's what happens. And next is fer.h5. H5 is the model trained file, the trained model that has been downloaded. Next is the dataset. Dataset is the fer 2013.csv.czip. So this is the dataset which I have taken from Tackle competition, which was there. So that I have taken it. It is, since you can see, it is a zip file. So what I'm doing is I'm extracting the zip file and deleting the zip file. So if you open over here, you will have fer.h5, which is the model file, fer.json, which is contains the model architecture, and fer.csv. .csv file is the dataset file extracted, and the zip file will be removed. Okay, let's go with the libraries, the multiple libraries. So very basic is the pandas and numpy for data processing, and OpenCV is the CB2 for image processing. Then Keras is for modeling, and these all is just for display options. That is fine. Okay, and so now let us import the dataset. See, the dataset is there in the image dataset is given in the pixel wise. So this is how the data set is. Let me ask them, can you explain download URLs? What are they? Yeah, that's what I explained so far. Yeah. Okay, I'll explain again. This URL is to download this file, fer.json. Just read the comment below. Comment above. This URL is to download this file. This URL is to download this file. If you want, you can check it. Just control click on it. You'll find it. So fer.json, and you can download it manually also, or you can download it through CLI. So that's what is. Hope I answered that question. Let I go with the data processing. I imported the data. I read the data. The data is like this. So emotion labels are 0, 1, 2, 3, 4, 5, 6. So there are 7 labels, and the label count is 0, 1, 2, 3, 4, 5, 6. And the pixels, if you see, each row has the pixel values. So there will be 48 into 48 into 3. This is the total dimension. These many pixels will be present in this row, and the usages, you'll have 2 types, which is training and public test. So training is the training data set, and public test is the public data set. So now we have to read all these pixel values and split into train and test. So that is what is the prepared data. Number of labels is 7. I'm repeating. Then we have to split the data into train and test. So I'm just creating a list for it, and I'm going to loop over. So what I'm doing is I'm going to loop over every single row by row, one by one. So that is for index run row, iter rows. So in the iter rows will iterate towards the rows, and you will get index value and the row values, row count. So the pixel dot split space, because this everything is a string. Okay, it's not an array or something. It is a string with a space separated string. So what I'm doing is I'm splitting it by spaces. Then after that, I'm appending to these lists. So xtrain dot append xtrain, and if it is a training, then appending to the xtrain, and ytrain is the labels. If it is a public test, is nothing but the x test, x text and test y.
So Abdul,
Okay.
what did these pixels represent? What were the pixels meaning?
Pixel values.
Are they positions?
No,
values.
pixel.
Oh, RGB value. Okay.
Yeah. It's just like an image. For every pixel has a value, right? So instead of taking a JPEG, I think they have created a CSV file, maybe because of this one to reduce the data limit or something like that. So it's like it is just 287. If you think, see over here, this file is 287. If it is a JPEG file, it will be large, right? That's why.
Okay.
There are more than 3,000, 4,000 images are there. So you can just think there will be too much data there. So that's why they have created a simpler CSV file. So that's what, for if it is a training, then append to train. If it is a test, append to test, that's it. If some error is there in the index error or something, you will get this error. That's what is here. So now next is, so all this is there in, it is a list. Xtrain, xtest, everything is in list. I'm converting everything to a NumPy array, and with a data type as a float, because we need floating point numbers. Then next is np.utils.non to categorical. This does the one hot encoding. I'm sorry, I'll change this. It's not label encoding, it is one hot encoding. We have 7 labels. So it creates a 7 cross 7 vector. So it creates for train label and test label both. Next is, see, we have see the data over here. The data ranges between 0 to 255 over here. That is a huge range. It is not normalized. Let's go for the question. One hot encoding means. Okay. I can explain that. Say that. So one hot encoding means it's like we have total number of this one is 7. Say that label is 0. For if the okay, let me not confuse. The labels are 1, 2, 3, 4, 5, 6, 7. We have 7 labels. So the one hot encoding, the value is so the value which is consideration is 1. So 1 is you have 1 at the first position, and rest everything will be 0. You will have 6 zeros. Yeah, this is equivalent to 1, and let's go with 0, 1, and 0, 0, 0, 0, 0. This is equivalent to 2. So like this it goes on. Hope this answers your question. This is one hot encoding.
And we do this to remove the relative numerical difference between 1, 2, and 7.
Exactly. So we are just saying that this all this label 1, 2, 3, 4, 5, 6. It's not ordinal. It is categorical. Ordinal means it says that 2 is greater than 1, 7 is greater than 1. So in our case, happy is not greater than sad, or surprise is not greater than neutral or something. We don't have any relation in between the classes. It's all independent categorical values. It's not ordinal. So that's why we do a one hot encoding. Got this. This will be used in our output layer. Yes. Output layer will be 1 cross 1 cross 7. That's why it is. Exactly. Yeah. Sure. Okay, that explains this. Next we are going with normalizing the data. So it is between 0 to 255. So we normalize between the 0 to 1. Basic normalization is this factor. So the formula used is x minus mean by standard deviation. Okay. So if you guys know Pythonic way, this is a very simple way to do this. If you don't understand, this means that x is equal to x minus mean, and x is equal to x divided by standard deviation. That's it. So this can be represented in this way. Hope you guys understand this. So np dot mean, it will give the mean of the explained data set. X is equal to 0 means it's like go in a row way. So that's what it means. Yeah, that's it. So this np.std will give the standard deviation. So after doing this, the values will become the extend and xtest values will become 0 to 1. Okay. So reshape the array. Reshape the array into 48 cross 48 cross 1. I'm sorry, like I said, 3 channels. It is 1 channel. It is a grayscale image what we have got in the data set. So the whatever this an extend xtest is there, we reshape the array into number of images. Number of images is the total shape of the data set, which is 3000 or something like that. Then what is the height of it, what is the width of it, and how many channels are there. Height and width is the 48 cross 48 resolution, image resolution. That's what is given over here. And so we reshape it in the way. So now next is number of features. Okay, we number of features and the batch size we have taken as a 64. Epochs we have taken as a 10 because I don't want you guys to run it for a longer time or something. And width and height is, yeah, we converted 3 channel to single one. No. I'm sorry. This is not a RGB image. It is a black and white image. So it is only 1 channel. So it has values only 0 and 1, 0 to 255. That's all. And only 1 channel. It is 1 channel. So black and white image will have only 1 channel. Color image will have red, green, blue, 3 channels. So that answers. That's why it is 1. It's a black image. Okay, cool. I got confirmation. Moving forward. Okay. The question was from Kartika was, it's like, well, why I have chosen a CNN architecture and why this architecture. So this is a very basic architecture. One is the intelligence is got from VGG16. What I have read is generally what people do is they take a VGG16. For people who don't know what is VGG16, VGG16 is a pre-trained model which has been already trained for this one image processing classification models and all. So what people do is they pick up the model and last final layers they remove it and train it. So what is seen is The VGG16 has too many dimensions, which takes into consideration of the color and multiple features, which is not required for emotion. Like texture and all. Texture and all is not required for emotion, not purely required. So these kind of features are makes the model overfitted. So that's why I didn't take up a VGG16, and most of the model I saw it is failing. So what I did was I saw a few articles which says that VGG16 is I'm sorry, yeah. So which says that the first few layers of the VGG16s are sufficient enough, and so I have just mimicked the architecture of the VGG16. That's what you can see over here. So if you visualize it, it is a pyramid structure. We see it in a convolution way, right? Okay, yeah, this is similar. This architecture is this model. You can just think about this. This is like a pyramid structure. This goes like from very big. Oh, sorry. So this will have 48 dimension, and this will have 7 dimension at the end, just like a converging way. That's it. So that's what is followed everywhere. Okay, that's what it is. So it starts with for this one dimension and ends up to final is a dense array, which is a 7-dimensional array. Yeah, okay. This is the architecture. You can change the architecture as you want. You can understand activation also, functions also. You can change it. Everything you can change. Like I saw the batch normalization didn't work out well for me, so I removed it. I have commented it. So it is just like a basic normal convolution, then another convolution layer, then do a max pooling and a dropout. Dropout I have given a very high dropout because this model was getting overfitted a lot comparatively as compared to everything. And then yeah, this is what. So
Abdul,
there
you
are
saying this whole architecture you designed custom?
yeah, it is custom only.
Okay.
It is not from.
Normally we'll take
I saw the
somebody's code, but in this case you designed it from scratch. Okay.
I did see multiple GitHub codes, but the architecture was like all VGG 16 plus layer, VGG 16 plus layer, and everything. Everyone was commenting it is overfitting, it is getting biased. That's what the stuff is there. Then I saw a Medium article which is explaining that. I saw the VGG 16 architecture and I just designed it. It's like it's a very basic convolution. You can change it to whatever you want, but it's giving a decent accuracy. So I was like, okay, fine. Yeah. So this is there. So an optimizer used is Adam optimizer throughout it has been, and loss is the categorical cross entropy loss because our labels are categorical, and we have a classification this one problem. So this is generally used over here. And yeah, and metrics to display is accuracy or calculate is accuracy. Next is okay, let's see how dropout layers helps in countering out of overfitting. Okay, that's a good question to ask. So what is a dropout layer? First of all, let me explain in this. So okay, so this is the first layer, and this is the second layer. Okay, we know that. So now when we put a dropout, we mean to say I have put for dropout as 0.5. That means I will randomly I'll just remove one layer. 50% of the connections I'll just remove. It can be this connection or it can be this connection. I'll just randomly remove it just because to learn more. How do I say? Okay, so one of the basic understanding or understanding of a CNN architecture is the first layer. First layer, this one understands the intelligence of the this one shape of the image. Hope you guys can see this. Maybe I can change the color of the pen. Yellow color should be fine. And so first few layers, it is clear. Few have said that it will take the shape of the, it will understand the shape of the image. Okay. So what if what if we don't want to how do I explain? Wait a minute. Give me a minute. So um, for two emotions, say for a face, for an emotion like happy face and a sad face, if you consider just the nose, just think the first layer, it is taking the intelligence of the nose, it is understanding nose. Okay, for a happy face or a sad face, for any face or something, the nose no, nose will not vary much. It will not for angry it might broaden a bit, maybe your nostrils are broaden a bit or something, but it will not, the variation will be very less. So what will it will not understand whether or the model will not learn which is a happy face, which is a sad face, when you don't install a dropout layer in between. Okay, instead you would install introduce a dropout layer in between. It would have learned only the half of the nose. It will not, it wouldn't have understood or learned the complete intelligence of the nose. So it will learn only the half of the nose. And in the next layer it will go full deep, it will go deep, and it will understand the relation between the nose and the eyes. What is the relations, nose and the mouth, how, what is the relations? So this is more hidden dimension or more deeper. So the dimension will help more. That is why, note the point over here. If you notice, generally the dropout layers so the dropout layers will reduce or will be maximum at the starting layers, and at the ending layers it will be very less. So here it is 50%, and at the last fully connected layer I have given only 20% dropout, because the more deeper you go, the more deeper you go, the more deeper is the intelligence is being seen. This the if you go, the top layers will understand only the high level intelligence, but bottom layer will understand the this one deeper intelligence of this. So that's why dropouts at the end layers or the last layers will be less as compared to the top layers. Good. I guess, hope I understood. Hope you guys understood that. Moving on. This is simple architecture. And then, so model.fit is very basic. You just give X train and Y train, then that size, and epoch is 10. Verbose is 1. Verbose is nothing that printing, how it's going to print and all, the way of printing. There is nothing. And the validation data to see is the test data. And I'm giving shuffle just again to not to overfit. So this is what it goes. So how it is getting trained, everything. So accuracy starts from 29, gets improved. So still it's going well over here. As you can see over here, it's not getting overfitted from for the 10 epochs, but later in stage, it will definitely, this architecture will overfit. One of the reasons is I was speaking something about data augmentation. I have not performed data augmentation in this, so I have just left you guys with that task. You can perform data augmentation on this. You can rotate it as someone pointed out, saying that like if it is can it detect a inverted phase or a upside down phase or something. So when you do data augmentation, it can detect that. It can detect everything like that. So make sure you do data augmentation on this data. I haven't performed. You can perform that. Then apart from that, you can change this architecture. You can make it more deeper, however you want. And yeah, that's how with the architecture. Let's go forward with the Lodino model. So this complete architecture, as you can see over here, what I have designed, there is no need to write all this code again in the test file. So what I did is I just so finally there is something called model.json. Yeah, so when you do model.json, it will this one complete architecture metadata will be saved to a JSON file, that is fer.json, and this file I'm just writing as fer.json. I'm just writing it. Then after that, I'm saving weights. That is what I have ran it for 200 epochs or something like that, and I saved the files as fer.h5. These two files I have uploaded to the Mega Cloud. Then I have downloaded it, so I will read it. So loading the model from JSON. Model from JSON is from the Keras only libraries. Just open this. I'm sorry. Yeah, just open this JSON file. You read this file, then automatically the model will be loaded. Model will be loaded. Model.load weights will load the weights of the previously trained model. Then next is I was speaking about har cascade, right? So it is the from OpenCV. Just open the cv2.cascade classifier and harcascade.xml file. So that is also provided. That's it. It's like phase harcascade. This is not required for collab. This is required for if you are testing in real time, because for collab the data set is there. The phases are already cropped. You don't need to crop the phases, but when you're doing it in the test file, then you need that. So when you do a model.summary, your complete architecture, what you have designed previously, that architecture comes over here. And as you can see, the final layer is 7. So final layer will be a this one. It'll be like a percentage if you consider. So 7 layers means, just think it'll be like 0.1 and something like 0.2, no, maybe 0.05 something, and 0.6 and 0.1, blah 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 blah, like this and all it goes. So the sum of everything should be what? Sum of this complete array. It will be 7-dimensional array, and it will be 1. So what this says is it just gives a probability distribution. Okay. So what we do is we pick up which is the label which has the highest percentage or highest value. In this case, the label will be this. So this position is third position. Third position, just think if the third position belongs to happy or something, then happy will be seen. I'll explain that. Okay, that's decided, explained. Now it is all about this one, testing the model. I'm going to test it with the same data set, which is the test data set. I'm sorry. Yeah. So this is matplotlib stuff and all. I'm going to loop over. I'm going to loop over 4 images, and I'm picking out 4 random images from the test data set. Then after that, so this is just reshaping the array. np.expand is just, so this array is in 3-dimensional, but this one data which is provided to the model is a 4-dimensional array. So np.expand does that, and model.predict.image pixels directly, it just predicts it. You get the predictions. Then after that, np.argmax. So argument. So I said, right. So this is how the this one array or the vector will be. You take the maximum out of it, and what is the index of it. So maximum is 0.6 and index is 3, or actually it is 2, because it's this one index starts from 0, 1 and 2 and 3, like that. So this is 0, this is 1, this is 2. So argmax will give output as 2, and 2 is nothing but happy or something. Yeah. So wait, let I go up. Max index. So find the maximum index. That is np.argmax. Emotions is this. These are the emotions. So angry is 0 and 1 and 2 and 3 and 4, 5 and 6. So these are the index numbers 0, 1, 2, 3, 4, 5, 6, and respective this one labels are this one: angry, disgust, fear, happy, sad, surprise, neutral. Okay, predicted emotions. Yeah, this emotions. I'm finding out which is the name or which emotion is it. So maximum index, I'm just finding out which label it is. Then after that, and I'm going to plot the image. So first is I'm creating a subplot, I'm creating a title. So title is the predicted emotion. What is the predicted emotion? You print it as a title, and after that you print the image. Then after that, this one image is there in 48 cross 48 cross 1, but Matplotlib and print will print, or it needs the data to be in 2-dimensional. So I did 48 cross 48, and since it is a black and white, I did a color map of gray. Interpolation nearest is it's to get a, since it is a 48 cross 48, and this one how we are viewing is it's bigger. So it is something like 128 cross or something. So very small or a low dimensional image, we are going to see it. So it will be very much not good, or it will not be visually good. So that's why I'm doing an interpolation nearer. That's it. And plt.axis is I just want to remove the axis that 0, 1, 2, 3, 4 and all. I don't want that. I just removed it. And plt show is going to show this. So this is the output. Angry, surprise, blah, like that. This is surprise. Angry is good, surprise is good. I guess this is not correct. The fourth one is not correct. So every time you rerun this code, new images will be plotted. Just because this one, what is it? I'm taking random images. So as you can see, this is happy, happy, neutral. This is sad. It's all plotting well. Okay. I'll explain the real time. So real time part is, guys, you have any doubts or something, drop it down. Just don't wait for me to end and ask the questions. You can just jot out the question anytime you want. So yeah, so when you want to test it on real time, like using your webcam or something, that time what you do is same thing. You load the model, you load the weight, then after that, see over here you need this one hard cascade to crop your face, just your face, and this cv2.video capture will just turn on your webcam, and you get this one. While true is you want to loop through every single frame of your video. So so this wall is there. So I explained before also, we don't require the color intelligence. So your webcam camera will be color image. We don't require that. So I'm going to grayscale it. So I'm going to convert the 3-dimensional or 3-channel to 1-dimensional. So RGB image to a gray image, like that. Then after that, face is detected. As you can see over here, face.harcascade.detect multi-scale, faces everything. So this is multi-scale, so that's why it can detect multiple faces in the webcam also. So this faces detected will be a list of multiple faces which is being detected. So this is nothing but x, y, and wh coordinates which is there in faces detected. I'm going to loop through that all coordinates, and I'm going to draw a rectangle for every face which is being detected at the thickness of 7. And after that, so I'm going to crop those images which is uh, from these dimension, cropping the region of interest, faces, images, like that. Then after that, I'm going to resize to 48 cross 48 because our model is designed to take the input as 48 cross 48. Then after that, image pixel, I'm going to convert the list into array, which is a NumPy array. Then again, I have said 3-dimensional to 4-dimensional. Then after that, this is nothing but normalization. So this is a min-max normalization. You can do. Previously I did a mean standardization, normalization, anything you want. So this is a min-max normalization. Then after that, this image pixel you're giving to the model, it's going to predict. Then after that, it's going to find which is the index which is having the high value. Then find out which emotion is there. Then a predicted emotion will have that. Then I have to predict this text. I have to put on the image or on the video. So I'm going to put the text over there at int x comma y. Int x comma y is nothing but the phase which is being detected. So this all is the font size, everything like that. So this is gonna print the text right above the this one box which is drawn, or the rectangle which is drawn on the face. So then after that, yeah, next is our this one, the output image will be a 48 cross 48. That will not be good, so I'm gonna resize it to 1000 cross 700 such that your window, you can see the video as compared to 48 cross 48. CB2 I am sure. Yeah, that's it. Then after that, this is to just quit. So when you press Q, it'll this one computer vision will start, or stop, emotion detection will stop. Okay, let's see the questions. Then after that, if you press Q, then directly just stop the webcam and destroy all the windows. It close all the windows, everything. Let us see the question. Why normalization ID done fixed divided by 1? Okay, fine. I'll explain that again. So pixel values, you guys know 0 to 255 is are the values, where 0 means this one black, and 255 no. Okay, something maybe a vice versa or something. So 0 can be black and 255 can be white, depends on that. So it's a grayscale image and the values will be 0 to 255. So what is a min max value? So min max formula is x minus min divided by max minus min. We know that minimum is equal to 0 and maximum is equal to 255. So this formula becomes x minus 0 divided by 255 minus 0, which is nothing but x divided by 255. Does that answer your question? Yeah, cool. Does expand dimensions convert 48 units? Expand dimensions, right? Okay, so before expand dimension, the shape will be 48 cross 1. So this will be the before expand dimension. When you do expand dimension at axis 0, it will become 1 cross 48 cross 48 cross 1. We need a 4-dimensional image. The model input will be a 4-dimensional, because this first dimension indicates that it is the first image, or the image count, number of images. It is only one image is being sent. Then next is height. Then next is width. Then next is this one, channels, number of channels. Since it is a grayscale, it is 1. Hope that answers your question. When we resize to upscale, don't we get distorted as against upscale? Yeah. Okay. Yeah, that's true. That's true. What we are doing over here is we are downscaling, then after that we are upscaling everything. But it is fine, just because the if you see in 1000 cross 700, the cropped image will be maybe some 100 cross 100 or something. So generally it's not like too much to think about, because that's why this model will work when your face is near to the webcam. When you go very far to the webcam, the images will get distorted, and yes, you say, as you said, it will get distorted and the values will not be good. That's there. Okay. Hope that answers everything. I guess I can run it on my end. Let's see. Python and what is it? Yep. Is it coming? Let's just wait for it. I guess it'll open now. Yep. Okay, good. Hey guys. Yeah, that's me. Oh, seems like I am surprised a lot. Yeah. See, I'm happy and surprised because of you guys. Yeah, this is the output.
Abdul, can you show me your sad face?
Sad face. I don't know. Maybe.
You're never sad. You're only neutral or happy.
What can I do? I'm just surprised and happy. Maybe you can try. A bit of
Yeah,
fear
my
is.
face will come sad all the time, I think.
Sorry.
My face will come permanently sad, maybe.
Okay, let's not get into that.
Okay,
Okay.
let's not go there. Yeah.
Yeah. So when you press Q, it gets stopped. That is there. You can test it with your faces. Maybe you can get. So see, there are multiple classes over here, and see, as you can notice, fear. The fear labels was getting repeated more. So it is somewhere it is getting overfitted a bit. So one is what I'll explain what all I have not done. Which if you plan to improvise the code or something, first what you guys can to do need to do is I'll just explain that. First is label imbalance. So just see if the amount of data provided for each label or how many images are provided for each label. So you can see that fear is getting repeated a lot. There can be high possibility that the labels with fear or the photos with fear, those photos are more as compared to others. So first is this, you do that. Then next is you do data augmentation to improvise, and what all you should do, data augmentation, then standardizing, everything is good. Yeah, then after that you improvise the structure, architecture, improvise the architecture. So yes, you can play around with the architecture, just try to increase the convolution or the deconvolution. Just do whatever you want. Use all your this one functions and stuff and all. So these are the three parts. If you improvise all this, then yeah, definitely the output will be good. So whatever the output I'm getting is around 60% accuracy or something. So even this one, this is a very old data set, and during that competition also the winner was something around 60 only, I guess. 60% was the highest accuracy, I guess, because the data was not that good. Maybe so. Yeah, you can't depend on purely on this data also. You can go with higher pixel data, and the higher the pixel you go, higher the resolution you go, the model will become more bigger and bigger. So it's your catch how much you download. That's me. That's all for now. Any questions?
Okay, that's great. So, audience, any questions?
I guess there is some error. I guess. Wait. What is this? No such file done. Okay, okay. I guess because of this JSON file and all, right? Okay. I guess I didn't do that. Just go here, guys. Download this file, fer.h5, fer.json file. 1 minute. I guess XML is also required. Download these files. So how will I share this file to you guys? So these Vivek, how will I share these files to them?
If you have a Google Drive link,
I guess I'll just share this whole folder.
you can send. You can share the whole folder, Google Drive link.
And this should work.